Thank you. I'm Pierre Desjardins. I'm the CEO and co-founder of C12. We are building a universal quantum computer. So there is clearly a quantum computing race, but it's not a qubit count race. So my talk today is just shifting the focus and talking about what really matters to build a quantum computer. And what is interesting is like the aspect or the form factor of like universal quantum computer will actually be defined by some core metrics that are inherent to the qubits that you are designing and building. And it's not only about like increasing the number of qubits. There is 3 other metrics that are absolutely essential to build a quantum computer at scale. Quality of the qubits. The second thing is connectivity. So how the qubits will be connected to each other. And the last one, very important, like how fast you can operate the qubits. So the clock speed, the unit operation duration. Quality, it's very important because at some point we will need some error correction scheme. And error correction scheme only work with a sufficient quality of the qubits. So there is like what we call a threshold. And if you are like below this threshold, you cannot actually build error correction. But what is also really interesting is that what's going to happen on the left of the threshold. And here, if you increase the quality of your qubits, you will need less qubits to have the same kind of performance. And in focusing on the quality of the qubits has a huge payoff. Like just think that if you have 99.9 fidelity in the physical qubits versus 99.2%, then you will need 100 times less qubits. So it has a huge impact on how the universal quantum computer at scale will look like. The second one is connectivity. Currently, all the solid-state architecture, so all the architecture of qubit on chip, they rely on nearest neighbor connectivity. So the qubit is only connected to its neighbor. But if we want to use more powerful, meaning more efficient quantum error correction code, we need non-local, or what we can say long-range connectivity. And also, this has a huge payoff in terms of how the universal quantum computer will look like. And last, clock speed. So when we are building quantum computer, we are building like just a different kind of quantum computer, but we want at the end that quantum computation be faster than any kind of classical computation. But if your clock speed is more on the kilohertz range, which is the case for some platform, then it will take like a couple of months to perform the same calculation that will be done in a few milliseconds with a gigahertz operation. So that's absolutely crucial in terms of how useful will be quantum computer. Now this is where C12 come into play. So what we are building at C12 is a quantum computer that are like no major roadblocks to deliver a useful quantum computer at scale. And we focus on 2 main things: quality of the qubits with our proprietary carbon nanotube qubits, and on the connectivity between the qubits, where we introduce a very special component, which is the quantum bus, that enable to have like more than nearest neighbor connectivity, so a high connectivity. And also very importantly, we are a semiconductor technology with a very small qubits. So, and this will have also a huge impact on how quantum computer, like at scale, will be used, very low energy consumption. So we were founded in 2020. I founded C12 actually with my twin brother. He imported the technology from the École Normale Supérieure. Currently, we are like more than 50 people, and we have done a lot of world-first research to build this technology. And one of the core assets is that we have built our own fabrication facilities. So we are like fully independent, and we can build completely our from end to end, sorry, our chips in our own fab. And actually, it's good because it's nano fabrication. So this fab is located right in the center of Paris, close to Pantheon. But the core benefit of this is that we have a process where we can build 10 times faster than if we outsource to the semiconductor industry. So where are we, and what are we building next? So 2033, we release Callisto. Callisto is a very powerful, noisy emulator that emulates exactly our quantum computer. This year, we're entering our first hardware product release with the first 5-qubit chip. And we target to deliver some first error-corrected quantum computer in 2030. And we are also working on a product roadmap where you will have much more detail on how we will achieve this in the months to come. Now, I guess in the room, you have also many industrial players who know a lot about quantum computing, but not sure really how this will apply to their business. And so what we have developed with Callisto is a whole set of methodologies and tools to actually identify quantum computing use cases, but also really create the algorithm, testing them, understanding how they will scale. And what kind of domain? So first, we focus on quantum chemistry and multiphysics, so simulation. So on quantum chemistry, we worked with Air Liquide on some very specific reaction and gas compound they need to deliver for the semiconductor industry. For the multiphysics, I'm very pleased to announce that we started a new project with Dassault Aviation on partial differential equation. Some problems that are way too hard for classical supercomputer. And also, we are working with Thales on an optimization problem. It's kind of a very complex optimization problem where the time to solution for classical solver are not sufficient enough. And our solution will also deliver some way to compute algorithm for artificial intelligence and cryptography, but we are not yet working with an industrial partner on this one. So if you are interested to understand and test how our technology can work for those use cases, but also on the other kind of use case, we would be very pleased to start working with you. Thank you very much.